Hello, this is George. I'm an IB physics tutor with IB++ Tutors. We help IB students globally get better grades. Today, I will explain second Newton's law of motion. Please subscribe to our channel for more IB-related videos. So let's get started with sharing my screen with you because I want to start PowerPoint presentation. Give me just 1 second. So here we go. Okay. As I have already explained, my name is George Koinakis, and let's get started with the second slide, which shows what is Newton's second law of motion about. Don't forget that Newton's second law of motion is a very common one, which means that most of the curricula, the international curricula, are based in terms of physics on teaching this law in detail. So let's start with the second slide. So we're talking about a virtual lab. You know that Newton didn't come up with this law just conceptually, theoretically. He studied it and tried to understand the way that all these things work by doing a lab. Of course, right now we're going to try to discover how Newton has worked by doing a virtual lab. Let's start it. It is based on GeoGebra software. So you can see a pulling force trying to move a box on a horizontal surface. Give me a few seconds to upload. So you can see that we can change the variables. When we say variables, let me show you. First of all, we can have the angle equal to 0 because we want a horizontal force for simplicity. And also the coefficients of static and kinetic friction must be 0. So we actually have a smooth surface to work with. And now the only variables that we're going to change are the tension, actually the pulling force, and the mass. Let's start by putting a mass equal to 2 kilograms and tension 4 newtons. As you can see, let's start it. You can see the object moving, accelerated at a rate of 2 meters per squared second. You can see that the acceleration the object has is 2 meters per squared second. If we pause it and reset it, now we can change the mass. We can put the mass, we can double it, 4, and start it again. And now, let's see, the acceleration has been halved. So we doubled the mass and the acceleration we get is halved, 1 meter per squared second. If we keep doing it again and again, we would confirm that mass and acceleration are inversely proportional quantities. Let's pause it again. And now it's time to play with the force. If we double the force by keeping the mass as it is, 4 kilograms, we get 8 newtons of tension. And we can see that the acceleration, which has been 1 meter per squared second, now has also been doubled. We doubled the tension, we get a doubled acceleration. If we keep doing it, it's obvious that we can see the acceleration being directly proportional to the applied force. So in this way, we can say that Newton has achieved to come up for the first, I would say, relationship. Let's go back to the presentation for now. Look, and here are the results. The first result is that the acceleration is directly proportional to the net force applied on it, and it is inversely proportional to its mass. I think it's clear according to the simulation we have just watched. And now, the mathematical expression, don't forget that all laws also have mathematical expressions, is that acceleration equals sigma f over m. Sigma f stands for the net force and mass of the object is labeled m. And now it's time for practice. In simple words, how should I work with this law when it comes to solving a problem having to do with forces, objects, motions, etc. I could say that we have 6 bullets, 6 steps to follow. The first one, draw the free body diagram. Sometimes it sounds simple, but it's not. Choose a proper system of axes. Here is a point of interest that we have to focus on. The positive x direction of this axis must be always the same with the direction of the motion. Third, resolve the forces, if necessary, on the system of axes we have already chosen. 4. Apply Newton's second law on x-axis, along with Newton's first law on the y-axis, if necessary. When I say if necessary, I will think that if you practice more, you will understand what I'm talking about. Sometimes we need it, sometimes we don't. Number 5, incorporate kinematics also if necessary. Sometimes dynamics are combined with kinematics, which means the concepts of dynamics are combined with the concepts of kinematics. It depends on the given data of the problem. And finally, solve the derived system of equations for the unknown quantities. And I'm having here a solved example. The source is the famous Chokos textbook, IB Physics textbook. And it says, calculate the tension in the string joining the 2 masses in the diagram. If the position of the masses is interchanged, will the tension change? And you can see that we have 2 objects and the force being applied on the right one. 60 Newton is the magnitude of the force, 30 kilogram is the big one, and 10 kilogram is the mass of the small one. You can see that I have applied here the first, the second step. I have drawn the free body diagram for each one of these objects. You can see W1 and W2 stand for the weights, the gravitational forces. N1 and N2, or you may prefer R1 and R2, N comes from normal and R comes from reaction. So it is what we call the normal reaction from the floor, from the ground. So we have N1 and N2, and the tension is supposed to be T1 and T2 at the ends of the string. But we know that when we have strings which are supposed to be, which are assumed to be massless and non-elastic, these 2 tensions are actually of the same, of equal magnitudes. And we have common acceleration A for both objects directed to the right. This is the free body diagram. We don't need any resolving components in this case, but in general, you may have 1 or more forces to be resolved on the system of axes we have already chosen. So, 4th step, we have to apply second Newton's law in the way I'm showing you. Let's start with mass 1. The net force sigma F1 equals M1 times A. And please pay attention at this point. In order to make the transition from vector analysis to algebraic expression, we have to take into account that the signs must be positive for F and negative for tension 1, just because we have assumed the direction to the right to be the positive. For the second mass, we apply almost the same, I would say, we repeat the same process. So tension 2 equals M2 times A. And also recall that I have already explained why tension 1 equals tension 2. As you can see at the bottom of the page, due to the non-elastic and massless string. And now, the final step, which is more math than physics, says that if we add the 2 equations, you can see that negative tension 1 and positive tension 2 will be cancelled. And we can see that F equals M1 plus M2 times A. We can solve this, we can rearrange and solve this final expression for A. We plug in the numbers and we get 60 over 40, which gives 1.5 meters per square second. The final answer is that the tension, if we go back on equation 2, is also 15 newtons. I think it's clear, isn't it? So hopefully I have helped a little with this law, but I would say that, first of all, thank you for watching this video. Please don't forget to subscribe to our channel for more IB related videos. Thank you so much. Bye-bye.